The second form for the equation of a parabola that you'll want to be familiar with after vertex form is general form. Now, before we get started, recall that vertex form is given by f of x equals a times x minus h quantity squared plus k. Again, we call this vertex form. Vertex form because it's easy to read the vertex right out of the equation. Now, if I were to carry out all the algebra, let's suppose that I square this binomial and then when I'm done, I distribute the a and I combine like terms, I'm going to get what's called general form. The general form for a quadratic function is given by ax squared plus bx plus c, where a, b, and c are real numbers. Notice this leading coefficient a matches the original leading coefficient over here. So I can still look at a to determine if the parabola opens up or down. However, I can't read the vertex directly from this general form. So how are we going to calculate where the vertex lies for a parabola in general form? To get there, we're going to have to do one of your favorite things, and that is complete the square. So let's look at our general form. What we want to do is work backwards and convert this back into vertex form. So to do that, we're going to have to factor a trinomial to get this term right here. Now notice, before we can complete the square, we are going to have to factor out the leading coefficient a, but I only need to take it out of the first two terms. So if I factor an a out of that first term, okay, here's my greatest common factor, that's going to leave behind x squared right here. Then I'm also going to factor an a out of this one to get b over a times x. Now, if that's a little bit confusing where that b over a times x came from, just work backwards. A times x squared gives me first term ax squared, and a times b over ax gives me b times x because the a's would cancel. And we still have our original constant c hanging out right here. So the idea there was just to factor the a as a greatest common factor out of the first two terms. Then inside parentheses, we want to complete the square. So I'm going to let that greatest common factor a hang out outside parentheses, and I'm going to work inside parentheses to complete the square. Now remember, to complete the square, we take the coefficient of our linear term, which is b over a, and we do two things to it. We divide it by 2 and we square it. Hopefully that sounds familiar from Unit 2. But instead of dividing by 2, since my term here is a fraction, I'm going to do the equivalent and multiply by a half, because it's easier to work with when you're dealing with a fraction, and then square. So essentially, we're dividing by 2 and squaring. Well, inside parentheses, we have b over 2a, and when we square that, we get b squared over 4a squared. So that's going to be the magic number that completes the square inside parentheses here, b squared over 4a squared. Now, in Unit 2, when we were solving quadratic equations by completing the square, we were very careful to add this new constant to both sides of the equation. But I want to keep my f of x alone and isolated over here. So instead of adding that number to both sides of the equation, I'm going to add it and then I'm going to subtract it on the same side of the equation. Now, what's tricky here is that I haven't actually added b squared over 4a squared to the equation. I've actually added a times b squared over 4a squared. That's a times b squared over 4a squared. Notice one of our a's would cancel, and we get b squared over 4a. So this combination, a times b squared over 4a squared, shows that we have introduced the new term b squared over 4a. So instead of, again, adding that to both sides, I'm just going to go ahead and subtract it right here, because when you add and subtract the same number, it cancels, showing that this line is still equivalent to and representative of the previous line. Okay, I know you're having a blast. Hang in there. The next step in completing the square is to factor our trinomial. So this, because of the way we formed that constant, is a perfect square trinomial. So we're going to factor it as x plus some number quantity squared. Don't forget, this number is the square root of what we had right here. The square root of that is b over 2a. And remember, that's familiar because we saw it back over here. And then if we get a common denominator and combine these two terms, we end up with this lovely fraction right here. All right, your day can only get better from here, right? After surviving that proof. So what's the point of all of this? Well, we took our general form and now we've converted it into vertex form. It's a little bit cumbersome, but it actually now is in this vertex form. So remember, in vertex form, I can read the ordered pair right out of the equation for my vertex. So I'm going to take this. This is now in place of the h, right? And remember, we changed the sign to get the x-coordinate of our vertex. So just by looking, we can tell that the x-coordinate of this vertex is negative b over 2a. Then we know whatever's out here, this is in the place of k, that's the y-coordinate of our vertex. But it's kind of a mess. It's hard to remember. So instead of memorizing that fraction, we're just going to say if I know the x-coordinate of my vertex, I can plug it into the function, and that should spit out the corresponding y value of the vertex. So here's the bottom line. What do you need to know? You need to memorize the formula for a vertex from general form. That is negative b over 2a, f of negative b over 2a. Okay, let's apply this to an example. On example 2, our purpose is to graph the quadratic function by plotting the vertex, axis of symmetry, x-intercepts, and y-intercept. So the first thing I want to observe here is the orientation of our parabola. Its leading coefficient is 1. Remember, we call the leading coefficient a. We're just going to observe that it's positive. So we know this parabola opens up. Then the next thing we want to do is find the vertex. Again, in general form, I can't read it out of the equation. I'm going to have to calculate it. So we're going to use our new formula, negative b over 2a, f of negative b over 2a. So it takes a little bit more work to find the vertex in general form. I'm going to do it one thing at a time. The x-coordinate of our vertex is calculated as negative b over 2a. So the a, b, and c from the quadratic function are the same a, b, and c we picked up for quadratic formula. So b is this coefficient right here. B is negative 2. So I'm going to record the negative from my formula, and then I'm going to replace the b with negative 2. Divided by 2 times a, which is 1. So it looks like we have positive 2 over 2, or the x-coordinate of my vertex is 1. So I'm halfway there. We also need the y-coordinate of the vertex. The y-coordinate is going to be calculated as f of negative b over 2a. Well, that means we're calculating f of 1, what we just found in the previous step. So I'm just going to go to my function and plug 1 in for x. This gives me 1 squared minus 2 times 1 minus 3. And when we calculate that, we end up with negative 4. So the ordered pair for our vertex then is x equals 1, y equals negative 4. As soon as we know our vertex, we can write the equation for the axis of symmetry. Remember, it's x equal to the x-coordinate of whatever our vertex was. So updating our graph, we have our vertex, 1, negative 4, and we have axis of symmetry at x equals 1. Remember, our parabola is going to open up. So if I begin to envision what that looks like, it looks like we're going to have 2 x-intercepts. So let's calculate those next. To find the x-intercepts, we're going to set y equal to 0, or the entire function f of x will get replaced with 0. So we need to solve the equation 0 equals x squared minus 2x minus 3. So if this is a quadratic equation in one variable, you could solve this by factoring, you could solve it by completing the square, or you could solve it by quadratic formula. I think the most convenient option here is factoring. This easily factors as x minus 3 times x plus 1. So we have 2 x values, x equals 3 and x equals negative 1. Each of those are the x component of an ordered pair with the corresponding y component of 0. So my x-intercept is 3, 0 and negative 1, 0. So let's go ahead and plot these on our graph. We have ordered pair 3, 0, and ordered pair -1, 0. And as I plot those, I'm always checking how do they relate to my axis of symmetry. They have to be equidistant from the axis of symmetry, so if they come out lopsided, I know I've made a mistake somewhere. Okay, we also need to find the y-intercept for this parabola, and to find the y-intercept, we set x to 0. So going to our original equation and replacing all of our x's with zeros, looks like we have a y-coordinate of -3. So officially, our y-intercept is 0, -3. So let's update that on our graph, 0, -3. Now that's sufficient information to graph the parabola, but I want to make sure my graph comes out symmetric. So what I'm going to do is use my y-intercept and observe it's 1 unit away from that axis of symmetry. So there must be a point on the other side of that axis of symmetry at the same distance away. That's the reflection of 0, -3. So I'm going to use that strategy just to fill out that point on the right side. And then I can construct a nice, smooth, symmetric parabola. And I'll be official and label it with its function, x squared minus 2x minus 3. Okay, good job. Let's try a couple more examples. On part B, we have the equation -2x squared plus 4x minus 5. So the first thing we want to observe is that the leading coefficient a is negative this time. So that tells me my parabola will open down. Next thing we need is the vertex. And remember, in general form, we have to use our formula. -b over 2a, f of -b over 2a. So starting with our x value, we'll calculate -b over 2a. So from our equation, we can see that b is 4. So we have -4 over 2 times a, and a is -2. So we have -4 over -4, or +1. Halfway there. Our y-coordinate is f of -b over 2a, which we just calculated as 1. And actually, since our equation is called g, let me correct my work here, we're calculating g of 1. So this gives us -2 times 1 squared plus 4 times 1 minus 5, or -2 plus 4 minus 5. And that gives us a y-coordinate of -3. So officially our vertex is ordered pair 1, -3. While we're here, let's go ahead and recognize the equation for our axis of symmetry. That's equal to x equal to the x-coordinate of our vertex. So we have vertex 1, -3, and x equals 1. Now I like to go ahead and plot my vertex and axis of symmetry before I work on x-intercepts, because if we're paying attention to what we learned about the orientation of this parabola, that is, the parabola opens down, it's going to save me a little bit of work. If my vertex is here below the x-axis and I can see my parabola is going to open down, then we can observe there's going to be no x-intercepts for this graph. So I can completely skip that work. Now, if I did go back and find the y-intercept, the x-intercepts by solving this equation, what I would find out is that it has imaginary solutions. So if you're not paying attention to the orientation of your parabola, you just kind of go to the next step to find the x-intercepts and you come up with imaginary solutions, you'd say, oh yeah, that means no x-intercepts. But watch for it so you can save a little bit of work. We are going to have a y-intercept because every parabola has exactly one y-intercept, and we'll find it by setting x to 0. So we have -2 times 0 squared plus 4 times 0 minus 5. Notice both of those two terms are 0, so it looks like our y-coordinate is -5. So officially, as an ordered pair, we have x equals 0, y equals -5. So we'll put that on our graph. 0, -5. And I'm going to go ahead and reflect this point to the other side of my axis of symmetry. That one has ordered pair 2, -5, so that I can connect those. I can make a symmetric parabola. So we have a tall, skinny parabola that opens down, and that's our function, g of x equals -2x squared plus 4x minus 5. Let's consider one more example in this section. The x-intercepts turn out just a little bit different. So one more example will certainly benefit us. So we have the function h of x equals x squared minus 3. Now this is a simpler function. I hope that you recognize we have our parent function x squared, which is our basic parabola, shifted down 3 units. So we can already begin to envision this particular parabola with transformations. But let's go through the process. Our leading coefficient is positive, so we know this parabola is going to open up. The vertex we could certainly calculate as -b over 2a, but again, thinking about transformations, this is our ordinary parent function y equals x squared, whose vertex is at 0, 0, shifted down by 3 units. So our vertex is 0, -3. We would find 0, -3 if we applied the -b over 2a formula to this one, but this process is a little bit more efficient. Our axis of symmetry is therefore x equals 0. So again, just to kind of reiterate what I'm thinking about here, imagine your x squared parent function. If I shift all of those points down 3 units, notice my vertex would land at 0, -3. And my axis of symmetry is right there on the x-axis with equation x equals 0. Let's take the time to calculate our x-intercepts. To do this, we set y equal to 0. So we're going to need to solve the equation 0 equals x squared minus 3. And we can certainly solve this with the square root property. So add 3 to both sides. I'm just going to go ahead and flip it around here. And then take the square root of both sides, acknowledging both the positive and negative roots. So we have x equals plus or minus square root of 3. So our two x-intercepts as ordered pairs will be negative square root of 3 and 0, and positive square root of 3 and 0. Those are the exact values for the ordered pairs of our x-intercepts, but I need to put these on the graph. So I'm going to approximate the square root of 3. The square root of 3 is about 1.7. So this is about negative 1.70, and that's 1.70. That helps me at least locate them on the number line, but I'm going to label them with their exact values. So my first x-intercept is about right there, negative square root of 3 and 0. And my second one, 1.7, is there, but I'm going to label it square root of 3 and 0. Also notice our vertex doubles as the y-intercept, so I don't need to do any more work on that. I can go ahead and sketch the parabola. So again, you see our parent function, y equals x squared. It's been shifted down the y-axis by 3 units. But with this new process, we're able to find the exact location of those x-intercepts.